BRATS, which is a great challenge. So my name is Andriy Myronenko, and I work for NVIDIA in a research group where we focus on the medical images specifically. And I have been participating in challenges for a while. So I wanted to start with this slide where for BRATS, I've started in 2018, which is here. And I have this photo with Spiridon, was organizing the challenge in 2018 at MICCAI 2018, which was in Granada, Spain. And I got the first place. And here Spiridon gave me a plaque, the award plaque. That was, I think, like 6 years ago. So at that time, they were giving plaques, which is like a heavy reward plaque, where I probably put it at work. So these days, you're not going to get any plaques. Most other photos are from more recent 2023 BRATS. And yeah, there's no more plaques. But BRATS has grown a lot compared to 2018, where maybe the whole challenge had 300 images, and that was the largest 3D data set and the largest challenge. So now, well, 5 or 6 years later, in 2023, it's not only one challenge for gliomas, it's multiple BRATS challenges with its own organizing committee and data sets. There is metastasis and meningioma and others. And most of these pictures are 2023 BRATS. This is the last MICCAI I attended. I didn't attend last year. But here's another picture with Spiridon again. So 5 years later, and you can see that a lot of scientific work has been done. The hair is more gray. But it's really nice. If you participate in these challenges, you will meet good friends from the older days. You'll meet a lot of new people, new students, and the international students. So you'll make friends from people from different countries. You can win a monetary prize now for each, specifically, let's say for metastasis, there was a $1,400. And in 2023, so I participated too with my colleagues, and we did well. We got out of these 5 tracks, we got first place in 3 of them, and a second place in the 2 of them. And here's Miriam, of course, and she's doing an amazing job for the BRATS. Yeah, so thank you so much, everyone who is organizing and participating. So these are BRATS, but I've also participated in other MICCAI challenges. So I listed here selectively some of them. And aside from BRATS, I've also participated in the FETA challenge, which was for 3D MRI brain segmentation, which was also the first place in Actor Segmentation Challenge 2022, which was a PET NCT segmentation. It was a pair of images, instant segmentation, ISLES, which was the second place. And the majority of challenges I did in 2023, I tried to participate in many, and myself and my teammates, we won the Kids Challenge, which is also a very large and long-running challenge for 3D CT kidney segmentation, shown here, and the first place in the 3D CT aorta segmentation and ultrasound segmentation of the heart, as well as BRATS. Like I said, in a 3 out of 5 tracks, and I was a second. So the BRATS, of course, is probably the longest running challenge at MICCAI, and probably the largest data set and the most famous, of course. Yeah, so these are different challenges. So hopefully I can share my experience, how to participate in these challenges and how to do well and how you can do well in the future challenges. All right, so why segmentation challenges specifically? So segmentation remains the main task in medical image analysis. And to support this point, I have this screenshot from MICCAI 2023 where they show the titles, the most common titles in the posters, paper submissions. So the segmentation here is the biggest one, together with image, medical learning. But usually the segmentation is the main task in medical image analysis. Even when it's not the main goal, it's a required component in some workflow. Now, this may not be true for other conferences, such as, or just like a machine learning conference or computer vision in general, like a CVPR conference, where there's another alternative directions. But for medical imaging, it is a very, the task is in demand for segmentation. Right. I'm gonna try, give me a second to present myself too. Let's see if I can do it. Okay, so let's try this. And so this is, I borrowed this slide from MICCAI 2022. There was a nice overview of challenges in general, and I don't usually see it in other MICCAI conferences. And so they were reporting what kind of challenges at that specific MICCAI, and there was only 38 challenges in 2022, but 70% of them were about segmentation. I think now the number of the challenges probably is 3 times larger. There's a lot of challenges, but the segmentation is still the dominant topic in these challenges. Another slide I borrowed from that presenter is they show the breakdown of these challenges. For example, the submission platform that people use. So the overall majority of these challenges are on a grandchallenge.org. This is where you would see like the leaderboard, and you would submit your results and maybe read the description of the challenge and download the data set. There's a somewhat smaller percentage at synapse.org, and I believe this is a platform that Bratz uses. Another interesting thing is the submission method. So in this 2022, the 57% of challenges required a Docker container. So this number is growing every year, and I believe, so my own estimate is most recently, probably the overall majority of challenges require Docker container, probably 90%. But initially, it wasn't that popular. It used to be an older system, very ad hoc, where even at Brett's 2018, they would send you in a limited period of time a small set of hidden data, and you need to process it quickly and send it back. So there was a very ad hoc system. But now you have to build the Docker, which is more fair, but it will take your time to build the Docker. So unfortunately, you have to learn how to do it. Where you're gonna find the challenges if you're interested, like I said, grandchallenge.org is a great website. I took the screenshot just yesterday. It lists all the ongoing challenges, not only MICCAI challenges, some other challenges as well. And even the past year's challenges, where you can join and download the data set. Maybe you don't need the challenge, but you can use the data set for some experiments. And of course, another great resource is actual MICCAI website. In every single year, you will find the link to the challenges that they approved, accepted. And this is from MICCAI 2024, the most recent conference. And you can see there's a lot of challenges. You can click on every one of them to read more about it. The Bratz is here at the very top. I recognize the FEDA challenge has been running also for a while. Some challenges will be the first time, some will be ongoing, and not all of them are segmentation, but many will be about segmentation. All right, so I have this slide about the challenges, which is versus the conference papers. So I assume there are students in the audience, and when they go to the MICCAI conference, they usually have some sort of a conference paper submission. So the challenges are a little bit different, which are also at MICCAI. They usually, you will have to write some kind of a workshop paper. But the differences are following. In the conference paper, you always need a novelty and main contributions. You need to specify your main contributions, and if you don't have them, even if the method is great, it's usually not accepted in my experience. So you need to prove you have contributions. So in a challenge, what's important is practicality. You don't really need your novel contribution. Everything works as soon as you maximize your rank or score. So you have a lot of freedom in your choices. Now, for a conference paper, you need to compare to other top methods, which is this part is time consuming and tedious in any conference publication. So you need to, even if you have your great method, now you need to compare to other people. So you need to track them down on GitHub, maybe download their code, try to understand what they're doing. But for the challenge, you don't need to compare to anyone. So it's easy in a way. But the time consuming part will be to build your Docker or whichever system the challenge requires at the end to submit. So if you're not familiar how to build a Docker, it will take some time initially. For the conference work, you will practice your research skills, and for a challenge, you will practice your applied skills. And then you'll get prestige if your paper is accepted. And here you'll get prestige if you're in the top. Now, arguably, I looked at the acceptance rate of the MICCAI publications, and it was 30% last year. And I think it's actually harder to get in the top, let's say, first 3 places in a challenge than to get a 30% acceptance at the conference, because your chances are higher here, and there's a lot of competitive teams, a lot of people trying to compete, so it gets a little bit difficult. And at the same time, the skills you will practice at the challenge are practically useful, because eventually you will be, depends, maybe you're a student, eventually you'll be working maybe for a medical device company where you need to actually produce a practically useful software or something that is working. Maybe you'll be working for a tech company, or maybe you'll start your own company, a startup, where your goal is actually to produce accurate results. And for the research papers, you'll practice your research skills, but a lot of it is not directly applied later. Right? All right, so I'm gonna give a lot of tips, somewhat disorganized about these challenges, but the first steps when you want to participate in a challenge is you register with it. Sometimes you need to sign some documents, which is simple. Then you need to download the data set and do open those images, at least a few, and just look through them. I usually participated in a 3D segmentation challenges, so I use the IDK Snap. Just look at them and then read carefully. One is dates. When is the actual deadline? And sometimes there are several deadlines. You need to submit preliminary paper, maybe you need to submit a Docker by a certain deadline. Very carefully read the metrics. So the metric is how they're gonna rank, your method compared to others. What is it necessary to win? How to win, basically. And each challenge will have their own system completely. A lot of them would have some sort of a dice in the mix, but there will be many other components. You can also read which data they use for the final testing. And you can pay attention, like if the data is maybe from a completely different hospital, then you need to think about domain generalization. Or if the data is very similar to your testing data, then it's easier. Read which evaluation system they use, is Docker required, and if it is, then what are their limitations on the GPU and the runtime? Because let's say they're gonna run it at the Grand Challenge website, and they have a limited, the limited number of GPUs, but each GPU is specific GPU. Like if you train your model on a large memory GPU and then you give it to this challenge website, and it will maybe crash because it's out of memory. And other things I always look for are the pre-trained weights allowed, right, in a challenge. So this is very tricky. If the pre-trained weights allowed, then you can download any pre-trained weights you can find from the internet and use it. So ideally, I like when the challenge doesn't allow these pre-trained weights, which becomes more fair for people. So then you focus on your method, and then you can compare to other people. When the pre-trained weights are allowed, then what people do is they download some very well pre-trained approach and just a little bit fine-tune it here, and then it's hard to see if it's performing well because of anything you did or those pre-trained weights. The same thing with it was additional data allowed. Like for the brats, for example, the pre-trained weights were not allowed, as far as I know, in 2023 at least. I don't know if it changed. And the additional data is it allowed or not? Again, like if it's allowed, then it also becomes a little bit challenging because some universities maybe have very similar data set or a lot of data available for them. If it's a large company, they maybe have access to some data set they can use in addition. And then some students maybe don't have this additional data, so it becomes less fair. I think for Brett specifically, there was 5 tracks, and I think one of the tracks were very smaller data sets, and they allowed pre-trained weights from another track to use in this track within the Bratts. So there was something like that. And of course, Google the previous year top submissions. If it's a challenge like Brat's, nothing stops you from just reading last year or year before what people did, what was the top performance method, what they did. You don't need to do the same thing, but you can just read what they did, what are the lessons they learned, and it's going to be very helpful. All right, the timeline. So each challenge will give you some kind of a timeline. So the brands gives you a nice picture of different milestone in this challenge. Some other challenges will give you a table or just a free-form text which you need to read. So let's look at the timeline. It was for Brett's 2023. There was a training data release in May, end of May. Then there's a validation release close to July. Then there's a validation phase where you can submit to this so-called preliminary validation board to kind of get a rough estimate how your method is performing. And you can correct me if I'm wrong, but that was my understanding. From July till August, you have a deadline for short paper submission. I always forget about this. They're usually a few pages, but you need to get them by this deadline before the testing phase. At that point, you may not even know your final method yet, but you need to submit something. ML Cube submission. All right, so this period from August, in August, this is ML Cube is a special kind of a Docker that Bratz is using, which to me overcomplicates things because one, you need to learn about the Docker itself, and then you need to also read for Brad specifically what is MLCube and what are the requirements to build it and follow its format. And if you participate in several challenges, that is going to be additional time investment to understand what it is. Testing phase. So this is where you can submit your Docker to the final testing set, which will be used to evaluate your final ranking. So this is the important part, actually. And then there's a time when you don't actually know what's going on. And finally, at the MICCAI conference, it's almost like an Oscar announcement where everybody's in the audience and you're hoping for the best and you're waiting, which rank are you are. But for other challenges, sometimes they actually tell you, they email everyone and they tell you, sometimes they tell you you're in the top 5, sometimes they tell you exactly where you are. Yeah, but for the Brads, it's usually a mystery. Let's see. Yeah, so timeline. Well, at least look at it. And again, like you probably, well, if you have time to spend from May to all the way till September, you can work on this challenge all this time. For example, for Brad's, I think I joined it in July during the validation phase, because you probably have like a limited time you can work on it. If you do have a limited time, join later, because there will be changes along the way. Suddenly organizers will come up with some cases that they fixed. Sometimes there will be cases, additional data released from some universities last minute. So if you do it later, you have a better data set actually. And this is true for many challenges. Or maybe they'll find some problem with some images they will correct. It's very often like this. And also the final deadline. In most challenges, they extend it. Usually the people would submit very last minute. Everybody's gonna wait until the very last day to submit it. Then the system get overworked. They couldn't get their Docker in. They will all beg for extension, and then there will be like a week extension. Well, don't count on it, but it happens very often. Okay, so metric to pay attention to. So yeah, so metric, you need to pay attention what is actually required in a challenge. So read what is used for ranking. And this is important for you for several reasons. One is try to use the same metric as a loss function for your training, right? If the challenge asks you like a metric is based on dice, for example, then use dice loss function, at least dice loss and something else, because you could, for example, use cross entropy loss. So you can train segmentation with cross entropy loss alone, and you will get good results, but you will not maximize for your what's important, right? And if it asks for the specific metric, so try to use it in training. Same thing with the details of the metric. For example, Brad's, technically it has three classes: green, red, and yellow, right? So there's three foreground classes of the tumor, but the dice will not be measured as average of this green, yellow, and red. What it will be measured on the three nested substructures. One will be yellow, which is enhancing tumor. One will be yellow and red union, tumor core, and the final one will be everything together, whole tumor, right? So if it asks you and then the average of those dices will be the final kind of dice. From my perspective, you will benefit of doing the same thing in your loss function. Just construct your loss function the same way. You will get these three regions and average those three losses. So then you're optimizing for a very similar thing what the challenge is asking you. All right. Another reason to pay attention to metrics. Download the Python code of a metric implementation that organizers provide. So a lot of times they say, okay, we're gonna use dice as a metric, and you're like, okay, I know dice. I have my own dice implementation on my computer. I have a dice implementation from MONAI, which is a popular medical open source toolbox, which we contribute a lot at NVIDIA. We're gonna talk about it later. So you have your dice, but the challenge implementation of a dice may be different. So just look at their code and in fact use it in your own evaluation. Okay, so here's an example of a lessons learned from one challenge. So really briefly, there was a challenge in 2023 for breast 3D ultrasound tumor segmentation here, which I participated. So the metric was based on a dice and a Hausdorff distance. So the Hausdorff distance measures how far away one surface is, the ground truth, from your prediction surface. And then these are the metrics. And then they average these metrics along all the test cases, and they finally give you the average result, something like that. But what happened is, in one of my predictions, the output was empty, completely empty, and the Hausdorff distance was, in their implementation, was infinity. And then when you average that with other cases, average was infinity, the final result is infinity. And actually, I got an email that we were excluded from the challenge because they couldn't evaluate it. Myself and a few other participants. So I appealed that, maybe just put score of 0 to that case, but I said it's too late to change the rules of the challenge. From the challenge organizer perspective, they had their rules and they stick to it, which is good. But from participant perspective, I missed that point. I didn't catch that case, and you spend time on training, and then you Docker, and then eventually you're not even evaluated. So that could be sad for that. Yeah. So look at the code that they provide. If the challenge organizer is doing it the first year, they will make mistakes. So especially pay attention there. For Brads, they're more seasoned, so it's more stable. All right. So again, if you look at the implementation of DICE, for Brads, there is some edge cases which you can take advantage of. Specifically for Brads, the Brads give a dice of 1 when you correctly predict no tumor, right? So the image has no tumor whatsoever, and you predict no tumor, you have this result of 1, which is not a typical result for dice, right? Usually you have your dice something, but there's one exception, and they give you this reward of 1. I don't know if it's interesting to people, but this is a screenshot from one of the brain metastases, which is a very small metastasis, very tiny tumor. So what are your chances to actually predict it correctly, right? It's very small. So your method will probably predict something else. You get dice 0. You can partially overlap, so you get maybe dice 0.5. So your chances of getting it correctly are small. On the other hand, if there is no tumor and you correctly predict no tumor, suddenly you get dice of 1. It's a huge reward. It's equivalent for you of getting perfect segmentation, right? So if you do a little bit of post-processing and predict something small and remove it completely, then some of those cases you will get reward of 1, and on average you're gonna do better, right? There is something specific to it, challenges, like in practice in a hospital. If your system thinks there is a tumor, you don't want to remove it artificially. You want to maybe show it to a radiologist to emphasize, like, pay attention to this spot. But for a challenge, you can maximize your chances this way. You can do a little bit post-processing, and you can do even cross-validation, how much of the threshold you can use to remove these small tumors as an outliers. For that specifically, this will help. Also, analyze your data. Well, for example, check, are there any cases with no tumor? Is it even a valid approach, right? Maybe every single image is expected to have a tumor, right? And then if your model predicts nothing, then you could threshold your probability such that you predict some kind of a tumor. You can think about it as well. All right, and finally, there are challenges that add the compute and time in the mix of all the other metrics. So this becomes very tricky. So I don't recommend these for beginners. One example, for example, is a Flare 23, which was also, I believe, a part of MICCAI. So aside from your traditional DICE metrics, they have additional metrics such as time between the Docker start and end, then the GPU memory used, and you get more points. If you, the lower memory, you get more points kind of system. So then you need to have a really low GPU memory. You really need to short time. There is a ranking in your actual accuracy of segmentation, and it's a multi-organ segmentation from CTs. And then you're not really sure how to balance it, right? And it's hard to understand where to pay attention. A lot of time, for example, I spent was on a simple things like a Docker start, like each Docker, when they start, they need to initialize into memory. And if your Docker image is large, such as NVIDIA PyTorch Docker, it's a 20 gig. It will start a little bit slower than a PyTorch native Docker, which is maybe 8 gig. And then if you want to optimize it further, you can build your own tiny Linux distribution Docker, and then you're focusing your time on something unrelated. Yeah, so in this challenge, I tried to it wasn't a great segmentation to save on time, and it wasn't it was an average on the memory. So at the end, I thought I was balancing an average everywhere, but the final ranking wasn't that great. Yeah, so on this, I'm not an expert, but if you like low-level programming, you can try in these challenges. Okay, data analysis. So it is important for you to analyze the data. Like if you don't have a system, just look at the images yourself, but ideally write a code, a script to kind of go through the images and collect some statistics. So we wrote this package called Auto3D SAG, which is a part of MONAI, which MONAI is an open source PyTorch-based project on GitHub for medical images. The first step there is a data analyzer, which will go through the images and collect different statistics. What are the average sizes of different organs? What are the resolutions of each image? In case of rats, they're already at the same resolution, but if you have CT images, they usually at very different resolutions. So you need to know how to resample them. What are the intensity ranges? If it's CT, are they all in the proper Hounsfield units? Or maybe some challenge decides to save them 0 to 1. So yeah, data analysis is important, and you could use one from MONAI. You can write yourself at least just to see what's going on with your data set. Data split. Okay, so this is more classical from machine learning, but you will need to do it as well for any challenge. So usually you have a training set, which is what you download from the challenge website. So you downloaded, let's say, 2,000 cases from a Brett's glioma. This is your training set. And then they have the testing set they don't tell you about, or some additional data. You can split this data set in 5 parts. Some people split it in 3, but the 5 is better. And you call the first part 20% validation and everything else training. Then the same way you can call this chunk validation and this training and this one. And then you can train 5 different models. And your validation piece is a little bit different. Yeah, so you have your cross-validation with a 5-fold. Usually you split randomly, but not always. If you have images, let's say from the same patient, maybe you have a patient and it has 5 images from this patient, those images are going to be very similar. And if you have that, you want to put those all images in the same fold, right? Because if you don't do it, and if you do it just completely randomly, what's going to happen is you train on 2 images from this patient and you have 3 images in your validation set, and your validation is artificially high, and you cannot really judge the performance of your method. So what you're going to typically see when you train it is maybe your training dice will reach 95%. You're going to train really well on your training set. Your validation dice on any of these validation boxes will be about 85%. And then when you finally submit, it will be lower than your validation by a few percent, maybe 82. So this is just like an example what you can expect. Right, so why do you need to split into validation at all? It's when you train. So here is the plot of training for 300 epochs. You train your model. At some point you will, and this is periodically evaluating your performance on the validation test, one of those folds. There will be a peak at some point, sooner or later, and then the model will overfit and go down a little bit. You want to catch this peak. Sometimes it will be quite a significant peak, sometimes a little bit, but it is better to catch this peak. This is why we're using this cross-validation. And so this is, you will train 5 different models for different folds, and their results can be quite different because your validation set in each of these folds is different. Some of them will be lower, some of them will be higher. But yeah, you want to catch those peaks. And so you basically keep the best checkpoint from each of these fold runs. Now, this is not always a good idea, and you can do without splitting at all. You can just take your whole training set and train it on everything. So let's think about it for a second. This can be advantageous if your data set is very small. If you have only 100 images, and then if you try to split it, then you leave 20 images and you train on 80 images, you do have your validation set, but you sacrifice 20 images out of 100, which is a large set, large amount. If you have 1,000,000 images, a very large amount, then you can split, and this chunk is very representative of the population of your data. But for a small set, it's not the case. So you're better off just taking the whole training set and train on all the data and think about it and just keep the last checkpoint. So you train blindly. You keep the last checkpoint, you will get the result. This result, actually, it's only 0.1% worse than this peak. So you lost a little bit of accuracy, you don't have a validation, but then you added more data to your training set, and that presumably will give you a better accuracy. So instead of these 5 folds, you train on the whole training set 5 times, and then you do the same idea. For example, for Brad's, there was one subset of data. I think the I want to say sub-African, which was very small, and for such small data sets, it's hard to split them because it's better to just use the whole thing, from my perspective. All right, and then usually when you start on a challenge or any new, actually in your research work, you want to approach a new problem, you want to do some exploration of ideas. I would keep just fold 0. You don't need to train 5 of them, and just try different ideas. Just start a bunch of training things for different ideas you have. They can be different loss functions, different augmentations, image normalization, learning rates, kind of like exploration. Just here's a TensorBoard plot of different runs. You can start and kind of get a feeling like which works better here. So this is your like initial exploration. From initial exploration, I'm gonna quickly jump to the final training. Another trick is you can train several times. You have your folds 0, 1, 2, 3, 4, so you can train 5 models, but you can train them 10 times each. Each time you train, you initialize from random initialization. And then maybe you keep 3 of the best models in each. You give 3 of the best models, now you have 15 models, and you ensemble on the 15 models. So why would you want to train several times, and why it helps? So look at the one-dimensional function, right? So your neural network is a function of many parameters. Here you have a single parameter, this dot. And you usually train with some sort of an optimizer which follows the gradient stochastically. If you start from this location, it will reach this local minimum. If you start from this location, it will reach this minimum. If you start from here, it will get here. In 1 dimension, in 2 dimension, you can see there are several possible local minima. And now this is 1 dimension, 2 dimension, but your network has easily 100 million of parameters. This is a 100 million dimensional search. It could be a billion of them. So when you start from a random starting point, you're gonna end up in one of these local minimum, and most of them are different but very similar results. So you're gonna get very similar results, but some of them will be much better than the others. I think it's almost, I think there was a paper calling it a winning ticket, where you, if you try it several times with a winning ticket, you get a better result. Yeah, so try several times, even if it's random initialization. Of course, this is more time consuming and requires more compute, right? So if you have more time for it, or if you have more GPUs available, this is in your advantage, definitely. Okay, and the bonus tip is you don't have to run 10 times randomly. You can actually initialize, restart from the previous checkpoint. Maybe you trained it once, get a checkpoint, train again, but you start from the previous one. This will be, in my opinion, even more advantageous. Yeah, but eventually you're gonna end up with some sort of a mix of models. Technically, the more the better, but there will be some requirements on a Docker to run a certain amount of time. I think 15 models is reasonable. Some people do 5, 15, could be more, could be 45. You and do use ensemble. Let's see if I have a slide about it. So ensembling, pretty much all the submissions to the challenges will use the final ensembling technique, where they ensemble several models together. This will increase your accuracy by 1 or 2%, pretty much always. And yeah, so it's a must use final thing. So if you train 5 models, for example, 1 from each fold, you have 5 models, you will run it through a new image, test an image, and then there's a common assembling techniques. One is an average. You average probabilities, so you will have 5 results for this image, you average probabilities, and then find the segmentations, which is a preferred approach in my view. And there is a majority vote where you first get the segmentations and then you majority vote for each voxel what it is. If the 3 of your results think it should be green and 2 red, and then you take it as green, right? Majority vote. There are other arguably better techniques. You can do a weighted average. If you can estimate these weights, so you have 5 models, if you weight the average, it will be better, but you need to come up with a strategy of heuristic how to weight them. You can also, in an ideal world, all your models are performant and the average is good, but sometimes what happens is one of your models, let's say fold number 3, fails for no reason. It gives you empty result. Maybe it wasn't trained correctly, maybe just confused. So now, if you take this empty result and all the other models gave you something reasonable, and then you average it evenly, then your output is going to be not good. You almost want to detect this case and remove it from average and average on the other 4 if you can. But yeah, so weighting, some sort of a weighting is advantageous. And then the bonus tip here is you can ensemble completely different models. It doesn't have to be only one model trained on several folds. You can train one convolutional neural network, you can train one based on transformers, you can train whatever you want and assemble a combination of them. Okay, so the method choices, like what is the actual algorithm you want to use? So this is a very broad topic, and there's many options. But typically for segmentation, it will be some kind of encoder-decoder architecture, such as UNet. So UNet is usually a specific paper, in my understanding, but the architecture they use is encoder-decoder. You can put transformer blocks in this structure as well. Most people will use PyTorch on GPUs with either MONAI or NNUNet, a very popular approach for segmentation, and build on top of it. So typically in these challenges, you will see people use something existing and they will adjust a few things and tweak a few things, pre-trained weights. So like I said, it's rarely allowed in challenges, but if they do allow pre-trained weights, then do use it. It's almost like a must for you at this point to use. Like if they allow pre-trained weights, if it's a 2D segmentation, you can try SAM weights or Dyno V2. It will give you a substantial boost. For 3D, there's not so many pre-trained weights, but you can use Vista 3D. This is from our team at NVIDIA. For CT, multi-organ segmentation, and there's some others. If you don't have if the pre-trained weights are not an option and you're just building it from scratch, then your typical dilemma is something based on convolutions or transformers. And I see this discussion very often. But in practice, in the recent MICCAI challenges, especially for 3D images, the top solutions are predominantly convolution based, not transformers. And there are reasons for it. So this is my personal view on the why usually conv nets perform better for this. So the transformers really shine when there's a very large amount of training data. Where there's like a million images, they really shine and can perform well. But conv nets, they have these inductive biases and they are suitable for smaller data sets. They will do better if the data set is small, and for medical data sets, they're usually small. If you train it from scratch, the transformer-based architectures, they're GPU memory intensive, so you cannot fit the whole image, you can fit only a specific patch. So typically you would have a patch of 128 cube, and so you random crop 128 cube from this image, which is a small cube, and you train based on this small patches. And if you think about it, instead of seeing all the organs, your network is seeing a little piece. So it's harder for it to learn the training. Whereas with convolutional networks, you can fit a bigger patch, like twice bigger in each direction, sometimes 3 times bigger. So it sees a larger window. So it actually learns better. Also, it's slower. Just to run training, and it's faster with conv-nets. So this is not super important if you do like a research paper, but for challenges, it becomes important because during the one run, you run your transformer segmentation, you can run maybe 10 different experiments with conv-nets. And then because you're exploring your ideas, you can just explore so many more ideas. Maybe eventually the transformers will give you better results if you have unlimited time, but your time is limited, so your exploration and hyperparameter optimization will be better, so you're gonna get better result. So this is my personal view. Yeah, so for medical images, specifically for 3D images, you cannot fit the whole image on your GPU in memory, so you need to random crop a small chunk. Let's call it a patch. So you need to decide how big of this patch you want to do. And my advice is to take as large as possible that fits into your GPU, so you cover the larger area. Because you take the larger chunk, your batch size, you have to compromise on your batch size. Your batch size becomes small, 1 or 2 is okay. Very small batch size, because you do want to, it's my opinion, you do want to put more information into a larger patch. All right, and then during the inference, this is during training, you do random crops with these patches, but during inference, you will have to take this patch like a square piece and slide it over the image and do multiple inference and then stitch together this. Now, you could write it yourself, or you can use a handy implementation, let's say from MONAI, which will do it for you. You just provide your model and your this patch size, and it will slide around and assemble everything together, so you get the output. And I wrote most of this class, and many people helped too. So when we write it, we optimize for memory usage. So this class will have to transfer between the GPU and CPU memory periodically and manage it and not to crash. So if you want to save time, definitely use some components from MONAI And this is a very useful class. I recommend it. This is actually the beauty of MICCAI. You don't need to use large packages. You can just use actually what you need. Maybe you write your own code, but you only want to use this because you don't want to reinvent this part. There's nothing scientific about it. You just need a good implementation. Inspect your failure cases. So when you train and your validation dies, let's say it's 85%, then you can look what image by image, like which images is actually super low and why it failed. And just look at them and you will notice a lot of things. Like I would notice that CT format was incorrect. The challenge organizer decided to save it not in house field units maybe, and you relied on it. The orientation could be incorrect. Maybe all images is just upright, but one image is completely different orientation. So then, okay, maybe you need to check for it and correct that orientation during training. Sometimes there is some sort of metal artifact which biased your normalization. Suddenly your normalization didn't normalize image correctly. Maybe the image is too blurry, like, and your training set didn't have such a blurry image. And okay, then you can simulate this blurriness via augmentations and retrain. Patient has only one kidney, so yeah, this was my own discovery. For some cases, the method was failing, and I was relying on having two kidneys. I had this heuristic to find two largest connected components, and apparently, which makes sense, in some patients there's actually only one kidney. But it's usually you don't think about it ahead of time. But when you look at the image and it becomes obvious, and then you can adjust your method. Post-processing, so after, usually you would train some kind of a neural network, but at the end you can do post-processing. I recommend to keep it very simple, don't overcomplicate it. You can do a simple thresholding for tumors. For organs, you can keep the largest connected component, which is useful for large organs, like it's a liver, for example. You expect to find only one connected component. Okay, so do prepare to build a Docker. So this whole slide is about Docker, and sometimes it's even more complicated if it's ML cube. You will have to build your Docker, and usually it can be as built as 30 gigs. So it's a large file, right? Your Docker image, large file. You will have to upload it to Synapse website, which takes time, depending on the internet connection and the website connection. So you build a Docker, you learn how to build it, then you build it, you upload it, then there is a time wait for the system to accept your Docker, then they put it in a queue to run it, and if it's a last minute submission, a lot of people will do it, so you wait until it even starts running. This whole process can easily take a day. And then it fails. Pretty much your first submission will fail. Some pass to some files, it's incorrect. You didn't program something correctly, that the way challenge runs your Docker, or maybe it used more GPU memory than you thought your model is doing something. In one challenge, for example, they decided to give MAH file to the Docker, whereas all the training sets were in Nifty format. And when your Docker fails, you don't see the error log actually. You just get a message that it failed. And for a reason, the organizers don't want to share anything that can reveal the hidden set. But at the same time, they don't give you the exact errors of your Docker. So you need to email the organizers. Sometimes you need to post on their forum in different challenges, and they don't reply sometimes they reply well, sometimes not. So this whole process is very time consuming. So yeah, plan ahead. In practice, everybody's going to be doing it last minute, but try to plan ahead. Okay, and I have an opinion about the preliminary validation leaderboard. So in all these challenges, they at some point before the final testing set, they open a preliminary validation board. It varies how it's named, but they allow you to evaluate your method on a small subset of data to give you a rough idea of your performance. However, this set is usually very small. In one challenge I saw, it was only 3 images. They open this public validation board. It runs your Docker based on 3 images. But participants made hundreds of submissions trying to beat each other on those 3 images. And then, so it gives you an illusion that you're improving versus other people, but you only improve in those 3 images. This will not be representative of your final test set, which is usually much larger. Even if your validation set, maybe it's 100 images, but it's still much smaller than a test set. So my recommendation is trust your own 5-fold cross-validation instead. So this is your internal work that you did. In BRAD 2023, I did not submit to preliminary validation leaderboard at all. I just skipped it. First, I didn't have much time at that time. It does save you time, but also if you do submit to these validation boards, then you have additional thing to worry about. You have your own cross-validation metrics, and now you need to reconcile how it looks compared to the different submissions you make to this leaderboard, validation one, which is usually small. There are exceptions when it can be useful. If this validation leaderboard is very large, then use it. Or if you simply want to test your Docker to make sure it runs without crashes, then I think it's also very useful. All right, so Monai is a very cool open source toolkit on the GitHub. NVIDIA contributes actively to it, as well as many universities. They have some real large packages, such as Auto3D which I and my team wrote, but you can also use some individual small functions, such as dice loss or different image loading functionality. I do have a practical steps how to use Auto3D and if we get to that point, I'll show you. You can, for Auto3D you can read the tutorial for brads and for kids. But in a nutshell, it's a system that uses many of these tips and tricks to automate it for you, so you don't need to do it yourself. It will analyze your data. It will choose more optimal parameters, like which crop to use for your GPU memory, which normalization to use. It will make some decisions. It can train several algorithms at the same time, transformer and convnet, and then choose which one is better, or you can choose just to train one of them. It will create automatic folds for you. It optionally has hyperparameter optimization. So it will use the steps under the hood. I did post on a Brett's forum before the challenge testing set how to run it with Auto3D and I'm not sure if people found it useful, but then I later used it myself. But to show you, we try to make it very simple. And this is the example of a configuration files. The only thing you need to run the whole training process. So I'm going to start with this FETA 21. This is a multi-organ segmentation challenge. All you need to specify is its MRI. You download your data set and you show where it is. You create a list of image and label pairs as a JSON. And then optionally, you put what are the names of your organs just for the tensor board to show it better. That's all you need. And you can run it with this command. Input YAML is your input file. It will run this whole thing automatically. For BRADS 23 specifically, you would have a little bit more lines, but again, there's MRI modality. You download your data set. You have a data list files of these image label pairs, which I'll show you how it looks. And for here, unfortunately, you need to specify these 3 structures because like I mentioned before, they want to compute dice based on whole tumor, tumor core, and enhancing tumor. And for this, you need to merge labels 1, 2, and 3 for whole tumor, 1 and 3 for tumor core, and enhancing tumor is 3. Very similar in kids, which is a kidney tumor segmentation, they also want to have 3 structures, and they want to merge labels 1, 2, and 3, 2 and 3 for mass, and 1, 2 for tumor. It's a different things, but it's actually very similar in a way. Yeah, so with these small configs, you can run the whole training. And I do have a demo how to run it. All right, well, thank you so much for listening, for all these tips and tricks. I hope you're gonna learn something, and I hope you're gonna do well in these challenges. I think it's a very cool experience to participate in challenges. It's very interesting, and yeah, if you do well and find something useful in the challenge, mention that you learned something interesting.
Thank you so much, Dr. Myronenko. That was fantastic. That was such a comprehensive overview of everything. And I just want to say that over the past week, as I was preparing for your talk, I'm reviewing a list of your work. And now my search history just looks like computer vision for beginners, semantic segmentation for beginners, encoder-decoder architecture for beginners. And I'm just slowly and consistently learning more about machine learning every day. And thank you so much for explaining it in so much detail to us. I do have some follow-up questions. So this question is from one of our team members who couldn't make it to the lecture today. And since you talked a lot about Dockers, I think this is an appropriate first question. What is the easiest and most painless way to containerize a model for submission to the testing phase? Would you be able to explain Docker principles to clinicians in a separate workshop, or is there any other software that can do the job instead?
Yeah, actually, it was somewhat new for me as well. I had to learn like any of you guys. The good thing is usually a challenge has an example Docker and how to build it. So download that file and just run it. They will have an instructions for you to create an example one, sometimes even with an example code to put inside. But overall, the Docker, it's like a small virtual machine. I don't know if I'm explaining it correctly, usually based on Ubuntu. When it runs, it can run on any machine, even on Windows, but inside it will run Ubuntu, and then it will run your code, and it has access to some input and output, and you need to read images from a folder and save it to a different folder. This is a nutshell. So they will take your Docker and they will run it in your cloud. It's like a containerized application. Yeah.
Okay. Thank you so much for that. I think we have some questions in the audience. Leonardo, would you like to go ahead?
Yes. Hi. First of all, thank you for your presentation. It was very interesting, and well, shed some light to like some tips that you might have for like participating in this kind of competition. Now, I wanted to ask something very quick that you maybe already said at the very beginning that I missed. Will the slide be available for the slides of the presentation?
The slides of presentation?
Yeah, will they be available?
From my perspective, yes, but I think they... Go ahead.
Yes, we have a Brat's YouTube channel, and we will upload this on our channel where you can access it.
Oh, very good. Thank you very much.
Yes, and you'll find links to all of our social media, links to our YouTube on our Twitter, LinkedIn, Instagram, Blue Sky, whatever. We'll make sure to keep you updated. Thank you so much.
All right. Thank you very much.
And next we have Mehmet.
And thank you for your valuable presentation. I want to ask. There was a writing in your slides for smaller brain tumors than 50 voxels about not including them. Can you explain that?
Yeah, so this is a post-processing technique, right? When you already got to the final result, you can do any heuristical post-processing. So specifically for breaths, like I said, if you remove if you output, let's say, no tumor, and it's not necessarily no tumor at all. Sometimes it's not maybe no enhancing component of the tumor. So you have still full tumor, but not a small part. If you happen to get it right, so you predicted no enhancing part and the ground truth has no enhancing part, your reward dice is 1. This is the very special metric that Brat's dice uses. So in your benefit to catch these cases. And the threshold 50 voxels is, it doesn't need to be 50. You can do the same cross-validation with 5 folds and try 50, 60, 70, 100, and see which one is actually works better. And just keep that one.
Thank you.
Thank you so much. Next we have Sarah.
Yes, thank you so much for your very interesting presentation. I also feel like I learned so much. And I have a rather simpler question that I think we get faced with a lot, which is when can we decide between the different folds we can choose from? For example, when would it be a better decision to use 10-fold cross-validation, and when would it be a better decision to use a 5-fold cross-validation?
Well, typically people just use 5. Well, if you use 10-fold cross-validation, right, then your validation set is very small. So it'll be in each of these folds is very small, right? And if you use only 3-fold, then the third part is very large. So then you sacrifice a lot for training. I feel like you need to have a balance, and 5 seems to be a good balance. That is very commonly people use. I wouldn't focus so much on this. You have so many other unknowns, which method to use hyperparameters. I would just stick with 5 folds.
Got it. Thank you so much.
Thank you, Sarah. I have another question. So in your opinion, what are the most common challenges that participants would encounter while using the current setup in Synapse for the 2025 challenge?
Specifically for Synapse website?
Yes.
I thought it was challenging to build this Docker, which has to follow this specific format, which Bratz requires. To me, it was new, and yeah, well, from my perspective, because the actual part with the algorithm development, I'm very familiar with, but this I had to learn and follow their examples. And especially if you're not an expert programmer with Dockers, that can be a little bit time-consuming. Yeah.
Okay, thank you so much. Also, what do you think organizers can do to support participants with less coding experience or just getting started learning coding? For example, like me and some medical students maybe who are interested in participating as well.
Yeah, good question. I think if you put on the forum how to achieve some sort of a baseline, there's another website, Kaggle, I didn't mention, which people use for challenges. Not only medical, not only segmentation, it's very diverse. But a lot of times they do have a really nice description. Here's the data set, and here's the baseline, the whole training steps. Like you can train this network with these steps, and you can achieve this model, and you're going to achieve these validation numbers. And the clear steps, and you can run it yourself. And here you have your baseline, and now you can, okay, I understand everything. Now I can build up on top of it. It's usually very clear, like the exact example, which is similar to the one I posted. I actually posted one on a Brat's forum, how to run it with Monai, which was like a tutorial example people can do. But that was from me as a participant. But if the challenge provides a few examples how to run it, that would be very cool.
Thank you so much. I will definitely look that up. If you don't have any other questions from the audience, I think we can wrap the session up. Thank you so much again, Dr. Myronenko. I can't thank you enough for the amount of knowledge you have shared with us today. And we absolutely look forward to having you again we have so much to learn from you.
You're welcome, Race.